Happy Friday, scientists, and welcome to Echo Live. My name is Anna, and I'm coming to you from the Michigan Science Center's Echo Distance Learning Program. Today, we'll be talking about simple machines. So before we get started with our activities today, go ahead and introduce yourself in the chat if you haven't done so already. The chat feature, as always, is your best way to communicate with me throughout the program. I'll keep an eye on that chat. I do see some familiar friends checking in already, so welcome back if you've been joining us for Echo Live every day so far, or maybe you're a recent joiner, or maybe today is your first time joining us. Go ahead and type in that chat feature. Let us know where you're watching from, maybe what grade you're in, or even maybe your favorite simple machine. So again, that chat feature is your best way to communicate with me throughout the program. At the end, we'll take some time for questions as always. So today we're talking about simple machines, and there are 6 main types of simple machines. We'll go over most of those today, and then we'll actually be creating 2 examples of simple machines that you can easily create at home using some pretty simple materials. So let's go ahead and talk about those examples of simple machines. We said there are 6 main types. The first simple machine that we'll talk about is an inclined plane. So an inclined plane is something like a ramp. It's usually triangular shaped, just like this, and it helps us to get objects from one point to another, or from a lower elevation to a higher elevation more easily. There's a good example of this. We have a mover pushing a box up into a truck, right? So rather than having to lift that heavy object up into the truck only using the power of your own body, this mover is actually able to move that box up the ramp or push it up the inclined plane to make that job more easy. So that's really the role of simple machines. They help us to either accomplish tasks more easily or to change the direction of a force that we have to put on an object in order to accomplish a task. The next type of simple machine is a wedge. Now you'll notice an inclined plane and a wedge look pretty similar when we talk about them just based on shape. So both of these come to a point. So we can see that there's a point down here on the wedge, but the purpose of a wedge is very, very different. So even though this wedge, if you were to flip it down on its side, could also act as an inclined plane, when we're talking about a wedge or how it's used, right, a wedge is designed to split apart 2 objects. A really good example of this, right, is when you're splitting firewood. So an axe is shaped like a wedge, so it comes to a point so that when you swing your force downward onto the wood, we can actually push those 2 sides of the stump or the log apart from each other, and that saves us a lot of effort, right? Could you imagine trying to grab onto 2 sides of a log and actually rip them apart with your bare hands? Certain strong people can do that. If you've ever seen one of the shows where they show off amazing feats of human strength, we know that it is possible, right, in order to rip apart logs or even to tear apart phone books. But for us regularly strength folks like myself, I'd rather use this simple machine, something like a wedge, like an axe. Our next type of simple machine is a lever. Now, levers are super important. And you'll notice that this actually has 2 components. So collectively, these 2 pieces make up a lever. A lever has a flat surface or a long surface that's balanced on what we call a fulcrum. So this green picture of a lever looks a lot like a scale or something like a balance, right? And so that fulcrum is the point where the beam would rest on. So that fulcrum, right? If we were balancing 2 objects that were of equal weight, we would want the fulcrum to be right in the center, like it is in this diagram. But if we're using this lever in order to lift something or pry something, like in this picture of the hammer, right? We may need to move that fulcrum either towards or away the point of us putting force down on that object in order to make that job more easy. So we can see that we have the hammer here, and if you see the direction of the force, it's actually pulling up and over. The point of contact with the wood would act as your fulcrum, and then we're actually able to pull the nail out of that piece of wood more easily. Next, let me turn off my video here, make sure I'm not in the way. So our next simple machine is a wheel and axle. And if you have ever ridden in a car, we know just how helpful wheels and axles can be. Before we had wheels and axles, right, could you imagine dragging or pushing objects across the ground? Wheel and axles allow us to roll objects around. But this isn't just used in cars or vehicles. We also use wheel and axles in many other ways. Things like a door handle, right? So the actual handle that you turn would be your wheel, but that turns a center axle inside your door, which will actually cause the latch or the bolt to push in and out. So we turn this rotational force into linear force in the axle. So we can use this in vehicles, but in lots of other daily household objects or mechanical machines as well. Next, we have a screw, right? So screws are also, one part of a screw is actually an inclined plane. So if we talk or if we look at screws, or if we were to blow this up to a really, really large size, a screw is really just a wheel and axle that has an inclined plane wrapped around it. That allows it to kind of combine some of these forces that we've talked about. You can use screws, right, to secure objects. So by pushing or rotating the screw into something like a piece of wood, right, we could secure two things together. But we also can use that if we're not necessarily using a screw, right? But even the lids of containers also have these inclined planes wrapped around them, which allow us to secure on caps and lids. And so screws are very, very important. Lastly, we said we had 6 simple machines. So very lastly, we have pulleys. And pulleys are a great example of how we can actually change the direction of the force required to do a job by using a simple machine. So if we look at this example or this example, we know that if we were trying to lift this bucket, right? Let's say we need to lift it up to a high distance or to a high altitude that we couldn't necessarily go stand on, right? We need another way in order to change the direction of the force, right? So if we couldn't necessarily stand up here on this beam and pull up on the bucket, right? We could use a pulley so that we can actually lift the bucket from the ground. By lifting a rope over the pulley, which is this round object right here, we can actually change the direction of our force so that by pulling down on the rope, we lift up on the bucket. Same thing works inside a flagpole, right? By pulling down on the rope, we lift up on the flag and can raise it really high. When we're ready to bring it back down, right, we can pull back down on the rope, and it works as a system. So we've talked about our 6 types of simple machines, but let's go over some examples of simple machines that we could make at home. It's Friday. I think it'd be super fun, even though the weather's not ideal here in Michigan, if we could come up with some science activities or simple machines that we could build inside our own homes. So I have our first example, which is creating a lever. Now, before we show you our lever, tell me what is an example you know of a lever. So in our diagram, we talked about how a hammer or the pry bar on a hammer can actually act as a lever. So remember that the lever is a beam laid across a center point that we call a fulcrum. So tell me in the chat if you know another example of a lever. See that someone guessed a door handle, and a door handle was a great example of a wheel and axle. So if we need to pull back up our image one more time, we're looking for what is an example of a lever. Right here, this green simple machine in this diagram. We said the claw on a hammer is a really good example of a lever that we might use in our daily lives, or maybe not daily, but we might use at home. So tell me, what is an example of a lever? Zara tells me a seesaw. That's a great example of a lever, right? So it actually looks just like that green image as well. So a lever is a great example, or a seesaw is a great example of a lever. A light switch is another great example of a lever. Where it connects to the wall would be your fulcrum. A crowbar, yeah, so even bigger than a hammer. A crowbar is an even bigger example of a lever. So generally we say that the longer your beam, the more force we can get out of it. So a crowbar is just a big version of a hammer. So say you've got a really stuck in nail, or you need a lot more force, right? Having that longer beam will allow you to put more force on the fulcrum and pry things out of the ground. People tell me seesaw, crowbar. Yeah, a lot of you are thinking a lot alike. So we have a pretty fun example that's maybe not necessarily a household or daily object or example of a lever, but today we'll be building catapults to talk about how these catapults can act as a lever as well. So this only takes a few types of materials. For this, you'll need some popsicle sticks. They don't need to be colorful like these ones that I have. Let me turn off my virtual background because I did choose some green popsicle sticks here. So you'll need some popsicle sticks, some rubber bands, a spoon, or if you don't have a plastic spoon like this one, I can give you another example of an object you can use. And then, of course, what fun would a catapult be if we weren't using it to launch an object? So you'll need to come up with some different kinds of projectiles. So I've got a few things we can test here, like Hershey's Kisses or cotton balls, maybe even Skittles that we had seen during our candy chemistry episode, right? And so we said a lever consists of a beam and a center point called a fulcrum. And so the first thing we're going to construct out of our popsicle sticks is the fulcrum. So you'll want to take about 5 popsicle sticks. So I have 1, 2, 3, 4, 5. And we'll want to secure these together with a rubber band on each side. So we'll go ahead and I'll secure this side with a rubber band. Now, this is a great challenge in dexterity as well. You'll notice that I have to wrap the rubber band around a few different times by wrapping it around and then crossing it back on itself and then crossing it again. If you ever put a ponytail in your hair, you might be good at this skill. If you've never had to do that, it's a good skill to practice. If you can't figure it out, definitely ask an adult, maybe a mom, a grandma, a sister, a friend to help you, but you'll figure it out. All right, so we've got our fulcrum, and we said that the fulcrum is that triangular piece. Right now, this isn't necessarily a triangle, but this is where we're going to have our beam rotate across. So we'll need 2 more popsicle sticks in order to create the launcher of our catapult here. I'm trying to select 2 that are kind of flat, not too bent. A lot of these are kind of warped, as you can see. All right, now for this one, we only want to put, so there's only 2 popsicle sticks here, and we just want to secure this one on one side. So we'll take another rubber band, and we'll wrap it around, like we said, back and forth, so it's on there nice and tight. It's not going to slip off, and I've only put it on one side this time. We want to leave this side open, so that we can actually open up our 2 popsicle sticks and stretch them over our fulcrum. So you can see that I lifted them up, and I'm just going to slide my fulcrum down as close to the rubber band as I can get it without the rubber band coming off. So slide it in there really, really tightly. And then the trickiest part about building these catapults is actually securing your fulcrum to your launcher. Now, you don't necessarily have to. It works just fine just like this, but you'll notice that every time I do that, my fulcrum comes off just a little bit farther. If you don't want to let that happen, all you need to do is take one last rubber band and wrap it around this point back and forth. So right where these 2 popsicle sticks cross each other, we just want to secure them with our last rubber band. And so you just wrap across and then rotate and then wrap across. And if you make this cross that you see on mine, if you make sure that your rubber bands cross just like this, it will stop it from moving. And so you can see now that if I push down on my lever and then let it go, right now my fulcrum isn't coming off like it was before. So we've really secured it in place. So your fulcrum works just fine, just like this, or your catapult works just fine, just like this. But it's not great for holding your object. And so that's actually why I've brought our plastic spoons, because it makes it kind of difficult to launch without it. So what you'll need to do is take your plastic spoon, hold it right on top of your catapult. You want to try to line it up so that your spoon is as close to your catapult as possible. But when you're building your catapult, right, just like with any engineering challenge, you can always change the design and see if yours maybe works better than mine, works different than mine. Maybe it has more throwing power. based on what you choose to change about the design of your catapult. So I'm going to put one rubber band down there closer to the bottom and add just one more closer to the top. So in total, this took me 1, 2, 3, 4, 5, 6 rubber bands. If you don't have that many rubber bands lying around, you could always replace some of these with tape. So you could always tape together your fulcrum or use something that's not a stack of popsicle sticks for that. So you can always, like we said, you can change this. Even though this is the way we've outlined to build your catapult, this isn't necessarily the right way, right? There's no right way in an engineering design challenge. Your way could work even better. If you come up with an easier or a better way to build a catapult out of some household materials, make sure that you send it to us so that we can see it. All right, so now our catapult is fully constructed, but what good would a catapult be if we weren't using it to launch something, right? So we're really relying on this simple machine, this catapult, to act as a lever. So we've got our launcher coming across our fulcrum on this stack of popsicle sticks here, right? And that gives this simple machine a place to pivot. Now, a catapult works by converting potential or stored energy into kinetic energy, the energy of motion as it throws that object, right? So while we pull down on our lever, we've got a lot of potential energy or energy that's ready to be used when I release the lever. And it really does fling pretty well. So we'll start with something light. We'll start with our cotton ball here. We'll line it up just over here. We'll set our cotton ball down inside the spoon. And then all we need to do is just store up our potential energy and release. And it threw it pretty high, but not very far, right? Let's try a different object and see if we get a different result, right? So we're changing the weight. So before we change anything about our design, let's first just think about changing our projectile. So next we have Skittles. Obviously, if you're launching objects inside your house, make sure that you're not launching near anything that could be broken, and never use anything too heavy that might cause damage to anything inside your house, including your walls, your pets, your TV, anything like that. So Skittles are not super dangerous, and I've made sure I've kind of cleared the area around my launch zone. So all we need to do is pull down, store up our kinetic energy, and release. That actually bounced off my wall and came right back. So this worked really, really well. Once you've tested a variety of objects, right, then you can consider how to change the design of your catapult. I've built a couple other ones. So I also have a giant catapult that I made out of using these giant tongue depressors here. And you'll notice that the setup is the same, right? So I've still secured my fulcrum together with some rubber bands, linked them across the top, and then secured a spoon to the end. If you don't have a spoon, what you could do is glue something like a plastic bottle cap right here to the end that gives you somewhere to rest your objects. So let's go ahead. We'll try it with the cotton ball this time using our giant catapult. 3, 2, 1. Pretty good. Let me zoom out just a little bit. So this did actually work pretty well, right? Better for throwing this light object, right? So let's go ahead and try it one more time. 3, 2, 1. And then, of course, what fun would it be if we didn't try at least one of our bigger objects? So we've got our Hershey Kiss here. Go ahead and drop it into our launcher. Pull back on our fulcrum to store up that potential energy. And 3, 2, 1. So it still threw pretty far, right? But since this object's a lot heavier, it takes a lot more potential energy in order to get it to fly. Something else you can change, right, is just by changing the angle of your launcher. So instead of holding it flat on the table, you can always try to launch upright, or you can always prop an object underneath it and see if changing your launch angle will affect your trajectory at all, right? So as always, to turn these into an experiment, you need to change one variable at a time. So if you're going to change your angle, right, choose an object that you can keep repeating. So choose something like these Skittles, or maybe even pieces of cereal, right? And do some experiments by changing your launch angle. I even made a teeny tiny little launcher here. I'll admit it doesn't work very well, but it is really, really cute. And I just happen to have some of these teeny tiny little popsicle sticks laying around, as well as a tiny little plastic spoon. So we'll go ahead and we'll try that just one time here with our Skittle in 3, 2, 1. not thrilling, right? But maybe if you have a limited space to work with, or you also have some of these smaller objects laying around, right? You can change the design however you want. So our catapults, that's an example of a lever. Finally, let's talk about one other simple machine that you can try at home. Well, I've noticed that this week it has been particularly windy. And so I've actually had an idea to create a simple machine that we could use outside while it's so windy. So for this, we're actually just going to be creating a pinwheel. So if you've seen one of these before, right, you know, when it catches wind, right, watch what happens. It starts to spin. So I've got an example here, but tell me what example or what type of simple machine is this? Think about it. I'll put up our diagram of our simple machines one more time here. Think about it. What type of simple machine is our pinwheel? Think about our options here. We said there are three main types of simple machines. Is it an inclined plane? Is it a wedge? Is it a lever? Is it a wheel and axle? Is it a screw? Or is it a pulley? Let's see. Some great guesses here. Maybe the name kind of starts to give it away. It is exactly right. You guys mostly guessed it. It is a wheel and axle. Let me start my video back up there. It is a wheel and axle, right? So the pinwheel, even though it's not necessarily round, acts as our wheel, the object that spins. And then our axle is just that small point of connection where our pin goes through the pinwheel in order to connect to the rod or the pole behind it. So our pinwheel spins on an axle just like a wheel and axle would on a car. Now, what makes this unique, right, is that wheel and axles, normally we power them with a motor. We normally use a motor in order to turn the wheels on our car and get us to drive down the road, right? But this is unique because it can actually work in the opposite way. So by harnessing wind power, right, we can actually create power from the wind. So as our pinwheel or the wind affects these turbines like you see behind me, right, that rotational or kinetic energy that's stored up or converted, right, can be turned into electrical power that we use inside our homes. Now, a pinwheel is very, very simple to create. A lot of people, so for this, the most important thing you'll need is a square piece of paper. It's important that it's square. And you won't need to print off a template or anything like that online, because I can show you how to make a square piece of paper from any rectangular piece of paper. So I just have a plain piece of, here it is rectangular, so it's not yet square, but all you need to do to make any rectangular piece of paper square is take it from the corner and fold it on itself until it's flat along the bottom edge, just like that. So put it flat on the table, line up that flat bottom edge, crease it all the way down, make sure you get it nice and lined up. And you'll notice that now we just have this excess strip right here. All you need to do is you can either draw a line on it first to help you and open it back up, or you can just cut that extra strip off this piece of paper. So we'll just go ahead and cut straight down, leaving us with a square piece of paper. So if you ever need a square, right, very, very simple, easy to do. Now, this actually left us with one step already done. There's a crease down one side of the paper, and we're just going to crease it now in the opposite direction so that we have an X going across the sheet. So we've got a crease in one direction, and then if we open this back up, now we can see that X on the piece of paper. It's helpful while making these if you note where the center of your paper is. So right in the center of the X, I'm just going to draw a little dot with a marker or a pencil or anything you have. So I've marked the center, and then we're going to need to cut about 2/3 of the way to the center from the outside edge. And so I'm going to mark that on my piece of paper here just by following the crease. about 2, didn't draw that one very straight, that's okay. So we said about 2/3 of the way, and then you're just gonna cut on these lines. That will create those blades that are able to trap the wind and turn the pinwheel like a wheel and axle. So go ahead and you just cut straight down the lines there. All right, now we're almost done with the setup for our pinwheel. So we've cut it apart. Now all we need to do is fold every other corner down to the center of the page. And this can be kind of tricky if you're doing this by yourself, but I've got a tip that can help you. So if you've got a partner that can help you with this step, you could fold this in and have your partner or your assistant just place their finger right on there as you grab every other corner. So you grab every other corner, and as you can see, if you're doing this by yourself, it is a little bit tricky. It's tricky to hold on to everything and keep it trapped right there in the center, just like this. So if you don't have an assistant to help you, what you can do is instead use tiny little pieces of tape. So I just got a lot of tape there, so let me go ahead and I'll just cut this into 4 little pieces so I don't need to waste it. All right, so we fold in this corner. So every other, right? So fold in a corner, tape it down, and then skip a corner. Fold the next corner, tape it down with your piece of tape that's stuck to my finger. Skip a corner. Fold the next corner down. Cut this one into 2 pieces, just like my last one. And then we only have 1 corner left. And we've created our pinwheel. So once we tape those down right, we've created basically the wheel part of our pinwheel here. But if you're holding onto it right, it's not able to spin around very easily. And so you'll need to create your axle. In this case, we're going to use a push pin. So make sure that you get someone to help you with this step. It can be very helpful to have an adult help you to push the push pin into some sort of soft object. So I'm just using a pencil that has a nice squishy eraser topper on it. And then all we're gonna do is just pick up our pinwheel, very carefully poke our pin right through the center, being very, very careful not to poke ourselves in the fingers. So pins are very, very sharp, be very careful. You can see it came right out the back of my pinwheel here. And then just carefully push it in to your eraser. You don't want to put it in there too tightly because, like we said, the object of this, right, is that your pinwheel is actually able to spin around. So we've created our pinwheel. Go ahead and zoom out here so that you can see. And then all you need to do is test it, right? And so folded mine in this direction. Make sure you're blowing into your turbine blades or into the front of them. Either one works. And here we go. Let's give it a test in 3, 2, 1. And it works pretty well, right? So you can use these outside to go measure how fast your wind is blowing, right? So if you were to take this pencil, you could even set it down in the ground and let it be outside, right? These are made of paper, and so they won't hold up very well if it's raining or snowing like it is where I live today. But this is a wheel and axle, right? We're taking that energy from the wind, just like in these wind turbines behind me. It's turning that wind power into kinetic energy. And that kinetic energy can then create electricity, which we can store as potential energy to be used for other projects or other devices. So those are our 2 simple machines. We've got our catapults and our pinwheels. So we've got a lever and a wheel and axle. If you're looking for a way that you could do these activities at home, rather than rewatch my video, we also post all of our at-home science experiments on the Michigan Science Center's website. So you can visit our website. It's right up here at the top, mi-sci.org. If you search for at-home science or type in /at-home science, brings you to this page with all of our different experiments that we've talked about so far on Echo Live. So if you're looking for a guide for how to recreate our popsicle stick catapult, all you need to do is come to this website and then click Open Activity Guide, and it brings you right to this page. It has a whole step-by-step guide, a list of materials, photos for how you can follow along. And it also has more detailed background information. So if you're looking to learn even more, these activity guides are great ways to do that. And then we also give you some challenge prompts on things that you can try later to really turn these into true experiments. So again, that's all here on our at-home science website. So we're just about out of time. I know that I love to talk and I always bring us right over our 30-minute mark, but if you do have any questions before we head out, please type them in the chat now. I'd love to answer a few of them before we head out here today, before you guys start your weekend. Hopefully you'll try to build some of these at home, but if you do have questions, go ahead and type them in the chat. Keep an eye out for them right now. So Jolie's missing my science, my space shuttle t-shirt. And I'll give you a hint that next week, there's a very special Earth and Space anniversary or holiday coming up. So if you can figure out which anniversary I'm talking about, maybe you'll be able to figure out which day I might wear my space shuttle t-shirt. So think about what anniversaries or holidays are taking place next week. And maybe you'll be able to figure out when I'm wearing that shirt next. I'm seeing some great questions. Someone telling us the definition of a screw is an inclined plane wrapped around a cylinder or cone. We talked about that. During our diagram, right? Great point, great observation. I see some people have figured out which holiday I'm talking about. Thank you guys all so much for joining us. Keep typing your questions in the chat. As always, we're gonna thank the sponsors of the Michigan Science Center right now. They allow us to provide these programs to you every weekday at 2:30 p.m. Eastern. So big thank you to Denso, big thank you to the DTE Energy Foundation for allowing us to bring Echo Live programs to you for free. If you are enjoying these, make sure you share them on your Facebook page. Make sure that you are liking and following the Michigan Science Center's Facebook page if you'd like to be alerted when we go live every weekday. And we won't see you tomorrow because tomorrow is a Saturday, and I know that we've got lots of experiments that we can try out this weekend, but we will see you on Monday at 2:30 p.m. And keep an eye out all next week for that very special holiday or anniversary that I'm talking about. So thank you all so much for joining. We'll see you next week. Enjoy your weekend.